So we're going to talk about two things. We're going to talk first about tension. And then with tension, we're going to talk about connected objects. Because if I connect objects, most of the time they're connected via a string. Occasionally, I think there's an example in the last practice where I just push on a ramp and they're not technically connected by anything, but they're resting on top of each other. And so they're connected in that way. But most of the time, it's connected with a string. So first thing, let's talk about the difference between an ideal, string, rope, wire, cable, anything. The only time tension isn't supposed to be something that's taken into consideration, and the only time we don't care whether it's an ideal something or not is if it's a solid object. So if I do say that I'm connecting something with this metal rod that's in the center table here, right? Tension's not a factor. I don't care if it's an ideal rod or an unideal rod. It is a rod. It cannot stretch. It absolutely has mass, but it can't be ideal. It's actually a physical object. In these cases, for ideal, we say it's two things. First, it has no mass. So an ideal string, rope, cable has no mass, and I don't have to consider its mass. The second thing it doesn't have is stretch. Both of those are important. An ideal string, I'm going to call it string, but it could be any of those things, does not have mass, and it cannot stretch. And for that reason, we can make this very important statement. The tension in the string is the same everywhere. Yay! That's the exciting thing. If I say that it's a massless string or that it's an ideal string, I can make both of those assumptions, and then the tension is the same everywhere in the row. This is extremely important. Tension matters a lot. On the day of the test, the day before the test, we're going to spend a lot of time reviewing, but I actually added an extra day in of review so that I can show you a 20-minute clip about why that is insanely important. It killed roughly 150 people. It's insanely important. Yeah.
What does that say?
Tension in the string is the same everywhere. Tension in the string is the same everywhere if it's an ideal string. Let's take this example. This is mass 1. It's attached by another string. This is mass 2. So this is two objects that are hanging on a string. If, right, both of these strings are ideal, right, then if I think about this as a system, I have to think about, let's say, what's the tension on each string. So if I say, what is the tension on string 1 and the tension on string 2, right? I could pretty easily figure this out. If I draw the free body diagram for M1, M1 would have its weight pulling on it. It would also have the weight of the second block pulling on it, and it would have FT1 going up. So FT1 would just be equal to M1G plus M2G. If I did the same thing for block 2, oh, it also has, I have to technically write it this way, FT2. And the way I know FT2 is M2G is because of that guy. So in reality, that's what it is. I cheated a little bit and said that it was just the weight, which it is because it's an ideal string. So I'm allowed to make that cheat because FT2, which is actually what's pulling additionally on M1, is equal to just M2G. The point is, with an ideal string that has no mass, this setup is pretty simple. right? I only have the weight of the boxes to consider, so FT1 is carrying both boxes, FT2 is carrying one box. Question about this. If I say instead that the strings also have a mass, so MS2 and MS1. Now, things change. So, I even can make a difference in saying, what about the top of string 1 and the bottom of string 1? What's the tension in the rope between those 2 points? What's the tension at the top and the tension at the bottom? So we'd have to think about this. If I draw a free body diagram for this first spot, it has all of FT1 pulling on it. All of FT1. FT1 would add up to what? FT1, you could draw all the free body diagrams if you needed to, but what all is on FT1 at the very top of this rope? What masses? M1G, M2G, MS2G for sure, and at the top of the string, MS1G. All of those things. If I talk about this point up here, if the strings are heavy, all of those are at the top of FT1. If I talk about the bottom, if I'm talking about drawing the free body diagram for M1, I have FT1 going up, I have FT2 going down, right? This FT1 would effectively be equal to mass of block 1, mass of block 2, plus mass of string 2. But no longer the weight of string 1. So this is what I mean. For an ideal string, rope, wire, cable, the tension is the same everywhere, so I can count on that. If I'm asking a question or working a problem, I can count on the tension in the string being the same everywhere. But if it's not, I can't. Because looking at these two free body diagrams, FT1 changed. It is different at the top of the string than at the bottom of the string. If they're really being evil, right? Try in your notes to write out what the force of tension would be halfway through the string. Right here. I did the top and the bottom. What if I did halfway through? Halfway through, it's not equal to this or this. What's the difference? It would half of what? Half of MS1, right? If it's at this point, I'll do it in pink. FT1 in the middle would be box 1, box 2, string 2, and half of string 1. Making what assumption? What did you just assume about the density of that string? Evenly distributed, right? What if the string for some reason wasn't? Which could easily happen because if it's stretched, right? If the string stretches and it stretches closer to the mass that it's hanging on versus at the top, or it stretches at the ends and not in the center, what just happened to the density of that string? It changed. They're not going to ask this question, don't worry. But it's something to keep in mind, especially if I'm headed to engineering, right? The tensile strength of that string, if it's actually a string or a rope, most likely it will stretch. And it will stretch and therefore have a smaller density at the ends and have a thicker density in the center. And that, again, now brings in the integral for linear line density of what is the center of mass of this rope now. How much is it holding on to, right? It becomes a hard question. So tension is really important. Understanding that we live in a world probably inside this classroom where ideal strings are what we do. But if we go out into the real world, we have to take that extra weight into consideration. And again, we're going to watch a video about when that went horrifically wrong and engineers didn't do their job correctly in a couple of days. Next week on Friday. All right, questions about tension. So that's the difference between ideal and non-ideal. On this, I would expect that wires and cables probably have less stretch. I'm not saying they can't stretch, but typically, if we're living in the real world, right, wires and cable are made of metal. They typically don't stretch as much as cotton fibers can. All right, let's go back to my pizza sign. I'm opening a small restaurant, and at this small pizza joint that sells only pepperoni black olive pizza, because it's the only one people should eat, and you burn it a little bit. You just burn it a little bit, put it on a thin crust, and it's basically a cracker. That's how I like my pizza. If you presented me with like a Domino's regular crust pan pizza or whatever, I would literally not eat it. All right, if I told you that this sign has a mass M, I want to know what that angle should be. I want to be able to figure out what that angle should be. Similar to what I asked on the first warm-up question today, I want to know what that angle is. So if I draw the free body diagram of my pizza sign, what force do I have going straight down? mg, right? Okay. Nice and simple. I have a force pulling this way of Ft1. Force pulling that way of Ft1. They are not the same tension. They're different ropes. I can't guarantee that they're the same tension. The question might state that, but I don't know for sure. And then I have Ft2. Okay, let's be careful here. Let's draw another free body diagram. Remember, again, for the second time in this class period, on AP, that's the free body diagram they're always asking for. Never changes. You cannot put components on an AP free body diagram. Components are super helpful, so I highly recommend draw this for the answer to A, and then when they ask you for B, go draw your second one. I'm going to change that because it kind of looked not like a square. Also, if you prefer dots because your first AP teacher taught you dots, that's perfectly fine. I don't care. I like squares because I know which direction everything's coming out of the square. A circle could be slightly ambiguous, but a square, no. There's 4 sides. Which side is it coming out of? All right, so Ft1's fine. Mg is fine. Somebody help me out. Ft2, what trig function should I put next to it, knowing my angle is up here with the vertical? For my horizontal component of Ft2, should it be cosine or sine? If it's up here, it's still cosine. So we got to be careful, right? This is still an angle with the horizontal. It's sneaky. You might think, no, it's a vertical angle because it's hanging out kind of like vertically, but no, it was still a horizontal angle with the x component. So, still cosine. And Ft2 is still cosine theta. All right, so our goal is to find theta, right? So let's write out our F net equations. F net x is equal to Ft2 cosine theta minus Ft1 F net y equals Ft2. Oh, nobody corrected me. I wrote cosine up there too. Sine minus mg. Which one should I solve for theta? Both of them have a theta. Which one should I solve? They're both equal to 0, right? Yeah?
The second one?
Why do you say that?
Because it's in terms of mg.
Yeah.
It's easier to...
I agree with that statement. That's my guess. Technically, though, I would have to get more information from the question. At the end of the question, it should say you can write it in terms of mass and gravity. Maybe it says you can write it in terms of Ft1. That would be a weird question, but sure. But does everybody see the difference between these two? In this case, I could have written out theta using either equation because both of them are equal to 0. But Onwall's right. If I write out this one, it's going to be in terms of ft1 and ft2, which is weird. If I write out this one, it's in terms of mg and ft2. The question could be really mean and just say you can only write it in terms of ft1. So then I would have to solve this side for ft1 and then plug it in over there to solve it. But let's say they just want it in terms of ft2 and m, physical constants. So I would say, all right, ft2 sine theta is equal to mg. So theta is equal to the inverse sine of mg over ft. A lot of times they give you numbers in these scenarios, like these questions. Oftentimes the mass of the pizza sign is 300 newtons and the angle it's at is 35, and they make you solve it from there. Questions about this? Okay, that's tension in a nutshell. All right, now we're going to do connected objects, which 9 times out of 10 means Atwood machine. I mean, really, truly, 9 times out of 10. It means Atwood machine. But let's clarify a couple of things before we jump into an Atwood machine. All right. Connected objects. The one true statement about connected objects, the most important one, is that what has to be true about their acceleration? These two objects that are connected somehow, what has to be true about their acceleration? Yeah. It has to be the same, right? They are moving at the same rate. That's why they're connected. That's the whole point. So that means that their velocities are equal, and typically, more importantly, their acceleration is equal. That's the kicker. They could say that these two objects are being pulled at constant velocity. That means they're both moving at constant velocity. Means both of their accelerations are 0. But really, this is the one we use most of the time. All right, basic example, I have mass 1 connected to mass 2. Mass 2 is being pulled with a force of F. The most basic connected object thing. And they want to know, typically, ft1 on 2, let's say. What's the force of tension from mass 1 onto mass 2? That's what they're asking for. Newton's third law tells me what? Newton's third law, anybody can quote it for me? An object. No, that's Newton's first law. I was trying to trick you. Okay, come on. For every reaction, there is an equal and opposite reaction. So, whatever ft1 on 2 is, the force of tension from 2 on 1 has to be the exact same thing. It has to be the exact same thing. So if they tell me that these guys are moving with constant velocity, even though it's asking for ft1 on 2, I might find, well, this is the force of tension of 2 on 1. It's the only thing acting on that box, right? It's moving at constant velocity, so what does the tension in the string have to be? If that's the only thing acting on the box. 0, right? It would have to be 0. That's a weird one. If it's accelerating, though, right? If it's accelerating, this is still M1. Then I could say M1A is equal to FT2 on 1. I write that all the way out. You're probably going to write FT, but I don't like to get confused. So if they don't tell me how much it's accelerating, I now have a problem. I don't know what A is, so I can't figure this out. So the strategy I do every single time in this scenario is look at the system first. If I write out the system, so the entire system, what is the only force acting on the entire system? F. Where did the forces of tension go? Where'd they go? They're internal to the system. And they cancel out, don't they? Right? They would cancel out, and now they're internal to the system. So I cannot use the system itself to find what they asked me for. That's typically always true. I can't use the system by itself to find what I'm asked for, because I don't know the acceleration and I need more information. When I look at the system, this internal force goes away because box 1 is pulling on box 2 with the exact same force that box 2 is pulling on box 1. Those are an equal and opposite reaction pair. So inside of my system, they cancel out. And my system just looks like this. So if I write out its F net equation, I have to remember it's a system. There are two masses, not just one. So what's the acceleration of this system? A would be F over m1 plus m2. So my question is still, what is the force of tension on box 1? Or from box 1 onto box 2. This force right here. On this guy. I'm using the last box in the system to do it. I did that for a reason. Why do you think I did that for a reason? Anybody? What would the free body diagram on M2 be? Yeah, Anma.
For M2, you'd have two forces.
Exactly. For M2, I would have two forces. I could directly solve for this, and that's fine. But on M2, everybody sees that I would have two forces, the force of tension over here and this force. So it just makes my life slightly more complicated. Since I know that the force on box 1 from box 2 is equal to the force of box 2 on box 1, I can solve for the box with less forces. That's typically what I do. So again, in a system of boxes, my best first thought is to solve the system first, then I'll always choose the box with less happening. Unless they tell me which box to look at. If I have to look at box in the middle, sad. All right, all I have to do is plug in the acceleration. F over m1 plus m2. And that's the force of tension of 2 on 1, which is equal to the force of tension of 1 on 2. Question. If I have a truck, I'm drawing a truck now. Oh, that's a bad truck. I've already started poorly. Okay, it became a very large truck. That's a truck. Haha. That's a truck. I don't know what I was doing over here. A truck is tied on to, I'm going to draw something I actually know how to draw, a camper van. That specifically would be an Airstream, because that's, or one of those really small, can only sleep like a mattress inside. I don't know what they're called. Anywho, a pop-up. It's either a pop-up or an Airstream, I don't know. All right, if this truck is accelerating, right? If this truck is accelerating, would the force of the RV on the truck, so RV on truck, or the force of the truck on the RV be bigger? Which one is bigger? The force of the RV on the truck or the force of the truck on the RV? I'm accelerating. This truck is driving forward. I am accelerating on the highway with my RV going to whatever campsite I am going to that night. What do you think? Yeah?
The same.
They are the same. Don't let me trick you. Don't let them trick you. They're the same. Doesn't matter if it's accelerating. Doesn't matter if it's constant velocity. Since this is an action-reaction pair, the force of the truck is pulling on the RV is pulling on the truck in the exact same amount. Don't let me confuse you, okay? Do not let me confuse you. Now, I'm going to draw a smaller truck so I have room for more things. Now I have a truck. I learned how to draw them. Took some time. And I have one RV. I'm doing this illegally. This is not United States freeway safe thing. But I have 3 RVs. One for me, one for each of my dogs. Okay. If this is the tension in 1, 2, and 3, which rope needs to be the strongest? Which rope is carrying the most tension? FT1, FT2, or FT3? Yeah?
FT1.
FT1, why?
Because it has to both carry RV1, RV2, and RV3.
Right. And so in reality, what force is it carrying? I mean, it's not vertical, right? So what force is this tension responsible for each RV? It's combating what force? It's not gravity, because gravity is taken care of by the normal force. Say it again. Who said it? Friction. Yeah, friction. So in a horizontal situation, there is still a force you're probably going up against. It would just be horizontal. Friction, sorry. All right. So let's work one of the Atwoods. Pick one from the connected objects. Look at all these Atwood pictures and decide which one is the scariest. There's lots of figures. Pick one that seems the scariest for the Atwoods. Whichever one we want to do. Take a vote. First one I get is the one I'll do. 8. Okay, we're doing 8. 8 is an Atwood machine on a ramp. That's so rude. It's not only a modified Atwood. If you don't know what modified Atwood means, let me be clear about the Atwoods. This is a standard Atwood. This is a modified Atwood. What we are doing is an extra modified Atwood. It's a box, sorry. Extra modified Atwood. This angle, I think they say, is 20 degrees. So I have mass, mass. Oh, it tells me what this mass is. This mass is 2 kilograms. 2 kg. So this question says, the figure below shows a block of mass resting on a slope. It said resting, so is it moving? Yeah, question.
We don't have the...
Oh, wow. I don't know where yours ran off to. Oh, it's behind there. It's behind. It's in the same packet.
It's not.
It's all not? Okay, well then here you go. Okay, there you go. Now the trick is that you have to read it to me. I don't have it anymore. What does it say?
Which one are we doing?
8.
The figure below shows a block of mass M resting on a 20-degree slope. The block has coefficients of friction 0.5, or kinetic coefficient is 0.5, and then the static one is 0.8. With the surface is connected via a massless string over a massless frictionless pulley to a hanging block of mass 2 kg.
Got it?
What is the minimum mass M that will stick and not slip?
Ah, perfect. So we're finding minimum mass M. That's what we're looking for. So what this is saying is that this block is not moving. Neither of them are, because remember they're connected, so whatever one's doing, the other one's doing too. So this block, none of them are moving. So this one on the ramp, not moving. If I think about the entire system, here are some really good reminders. When I think about drawing the entire system for an Atwood, the first thing I do is determine which direction is going to be my positive x. I typically draw them in positive x directions. If it's better for you and you like it, you can draw them as positive y directions. A lot of people do that because it's hanging. So their first instinct is to draw MG straight down. And so I wouldn't want to mess with that instinct. But you have to decide which direction my system is going to have. So if this is going to be positive y, okay, that's fine. That means mg for this mass here, which is equal to 20 newtons, we'll say. We'll round and use 10. So that's the mass of this 2 kilogram block. That's what's pulling positive y direction down. If you don't like that, make it negative y direction. It's fine. Down. On the other side of it, string is massless, pulley doesn't have any friction, so none of this matters. So on the other side of it, I'm up against whatever's going this way on mass M. So that would be, it's on a ramp. So what's the force on mass M going down the ramp? mg what? We learned about ramps. Sine or cosine? Sine. Sine theta. So on this side of it, I have mg pulling down. On this side of it, I have m. I also have friction. Okay? I'm preventing this block from going down. That's what my, or actually I don't know, do I? You have the question. It doesn't necessarily say it's at rest. So I don't know which way friction is going. Friction could be preventing this mass from pulling it down this way. So that means it's opposing motion, it's going this way, out down the ramp. Or maybe this mass is bigger and it's going, yeah.
Yeah, I think it says at rest.
Well, yeah, I know it's at rest. But that's what I'm saying. The friction is keeping it at rest. I just don't know if not at rest. I think the next part B maybe says it. But if not at rest, is it that M's going to slide down or that 2 kg is going to pull it up? That's the question. Up the incline. So that means that currently friction is preventing this from being pulled up the incline. So friction must be also going this direction. Here's the good news. If you don't know which way friction's going, you will figure it out. When you do the math, it will come clear. Any of these situations, if you're not sure which way friction is holding it, right, it will come clear. All right, if I write out that for the whole system, that means m plus 2, it's the mass of my whole system, times an acceleration of 0, oh, so I don't care about that side. Just want to be clear, the mass of the system is both, is equal to 20 newtons minus friction minus mg sine theta. So 20 is equal to mu s mg cosine theta minus mg sine theta. How did I get the friction force? I know it's at rest, so that's how I picked US. How did I know it was mg cosine theta? What told me that? Because it's on a incline, right? This box is on an incline. So its normal force is mg cosine, just like it always is on an incline. Yay for inclines. All right, I'm solving for mass. That's what I'm solving for. So I'm going to factor mass out. I get mass is equal to US g cosine theta minus g sine theta. All of that is numbers. So if I grab my calculator, mu s is 0.8. Oh, I'm graphing. 0.8. Gravity is 10. Cosine of 20 minus 10 sine 20. I get 4.1 actually. Mass times 4.1. So what is the minimum mass that I need to prevent this from moving? Roughly, we can do this math. Roughly, 20 divided by 4? 5. 5 kilograms. Sometimes I send you easy math questions to make sure you're still awake and paying attention instead of falling asleep. So that's the minimum mass I would need to keep it going. Otherwise, if I had less mass, my assumption is that it's going to pull this down the hill. So that would be bad. All right, we're going to stop there. Do the connected